In Chapter 6, we are looking at exponential functions. We are going to look at what the graph of an exponential function looks like, what the equation of an exponential function looks like, what the connection is between the equation and the graph of an exponential function. We are going to look at solving exponential equations, including those equations that arise from an application situation. Let's start by looking at 6.1 and 6.2, exploring the characteristics of exponential functions and graphs. An exponential function is a function in the form f at x equals a times b to the x, where a is greater than 0, b is greater than 0, and b cannot equal 1. Let's break down that statement a little bit. Let's start with the equation. So this is the equation of an exponential function. A and b are parameters, which means when we look at these functions, a and b will be numbers. A represents our coefficient. It is the number in front. It has big implications when we go to look at the graph, but A is our coefficient. B also has implications when we talk about the graph of an exponential function. B is the base, and x is our variable, and it's the position of x that's important. X is the exponent. And because our variable x is in the exponent, that is why we call these exponential functions. It's the position of the variable that tells us the kind of function that we are looking at. Let's break down now the little tidbits that are offered after. Let's start with this. A is greater than 0 and B is greater than 0. All that means is the coefficient and the base for every question that we do in this chapter will be positive values. So it doesn't matter what kind of question we're doing, the coefficient and the base will always be positive. That's what that A is greater than 0, B is greater than 0 means. B cannot equal 1 is explained right down here. B cannot equal 1. Since 1 to the power of any real number is equal to 1, the function would become a constant function and not an exponential function. So you will never see y equals 1 to the power of x. Because when we graph 1 to the power of x, what ends up happening when we graph it is it just becomes a straight line, horizontal, a constant graph through y is equal to 1. That is not exponential. So your coefficient and your base will always be positive, and your base will never be 1. Those are what we're dealing with when we deal with the equation of our exponential function. So let's go ahead and look at what the graph of the exponential function is going to look like. There are two different shapes of graphs of an exponential function of the form a times b to the power of x, where a is greater than 0, b is greater than 0, and b cannot equal 1. Case 1 is an increasing graph, or what we call exponential growth. When we have exponential growth, the curve extends from quadrant 2 to quadrant 1, and the curve is rising. So we have an example right here. The graph starts in quadrant 2. We notice that looks like it touches the x-axis, but actually it doesn't. It's getting really, really close to the x-axis, but not actually touching it. And then as we get into quadrant 1, it rises quite sharply and lands there in quadrant 1. We notice that with exponential growth, as the x values get larger, the y values get larger very quickly. And that's why the graph is rising as we move from quadrant 2 to quadrant 1. What makes exponential growth happen? It is reliant on the base. If our base b is greater than 1, then the function increases. If the base is greater than 1, we have exponential growth. So you'll notice that the two examples that are shown down here, 3 times 2 to the power of x, if we want to know if it's growth, or decay, we look at our base. Because 2 is greater than 1, this equation is showing exponential growth. The base here is 5. 5 is greater than 1, so this graph would also show exponential growth. These graphs would look a little different from each other. They're not going to look exactly the same, but they are going to have the same shape as the graph here on the left. All 3 of these functions are going to start in quadrant 2 and rise or increase as we go into quadrant 1. Our second case is a decreasing function, or what we call exponential decay. When we have exponential decay, the curve does the opposite of what it did in case 1. It still extends from quadrant 2 to quadrant 1, but this time the graph is falling. So here we are in quadrant 2, but notice that our y values are quite high in quadrant 2, and then they get smaller, 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 and then we are into quadrant 1, and again that graph not touching the x-axis. It's skimming along the top of the x-axis. It's getting closer and closer to it, but it never touches it, and we get into quadrant 1. Again, this is dependent on the base. If the base is positive, but between 0 and 1. So what that means is we might have a fraction whose numerator is less than the denominator, or we might have a decimal that starts with 0 decimal something. If our base looks like that, then we have exponential decay. You'll notice in the examples that are given, the base for this example here is 1/2. 1/2 is positive, but is between 0 and 1. So this function would show exponential decay. The base for this function right here, 1/8, also between 0 and 1, so exponential decay. These two functions, along with this function on the left, are all going to look a little bit different from each other, but they will all have the same basic shape. They will all start high up in quadrant 2 and then fall rapidly and then coast along the x-axis in quadrant 2 or quadrant 1. They will fall from one quadrant into the other. Let's go ahead and let's have a look at this chart right here. We are given 4 different functions, and what we need to do is we need to fill in the chart for each of these functions based on what we know, and we're also going to look at how to graph these on our calculators and get some answers that way. Some of these questions, though, we are going to be able to answer without our calculators, and that's where I want to start. We're going to start with growth or decay. So we just saw that growth or decay is based on the base or our b value. So let's have a look at each of our functions that are here. Let's decide what their base is, and then let's decide if that base tells us growth or decay. For this first one right here, our base is the 3. So our base is always the number that's below the exponent, right? It's our b value. So our b value for this one is 3. Because 3 is bigger than 1, this would be exponential growth. For our next function, our base is 1/3. 1/3 is between 0 and 1. So because our base is 1/3, because it's between 0 and 1, this would show exponential decay. F at x equals 7 to the power of x. Our base is right there. Again, it's always the one just below the exponent. Our base in this case is 7. 7 is greater than 1, which means this function would be exponential growth. And finally, our last one, f at x equals 1/5 to the power of x. So our b value there is 1/5. 1/5 is between 0 and 1. So this would show exponential decay. Now, we could also graph each of these and just look at the functions. If it rises from quadrant 2 to quadrant 1, it would be growth. If it goes down or falls from quadrant 2 to quadrant 1, it's decay. But we don't have to do that. We can just have a look at the base and answer that question without graphing. We can also answer this next question without doing any graphing. The next question says the number of x-intercepts. What we're going to find, and if we back up a little bit, we said that the graph never crosses or touches the x-axis. We said it gets super, super close. It kind of rides on top of it here and here, but it never actually touches or crosses the x-axis. What that means is there are no x-intercepts. So I can go ahead and write none for all of these functions. They're all exponential functions. They all look a little different, but none of them are going to cross the x-axis. They're all going to sort of skate along it. I'm going to skip the y-intercept question for 1 second. We're going to do that one by graphing. End behavior we can answer right away as well, because we know from above that the end behavior is almost the same for all of them. So for all of them, they all start in quadrant 2 and end in quadrant 1. So all quadrant 2 to quadrant 1, quadrant 2 to quadrant 1, and the fourth one, quadrant 2 to quadrant 1. But we're also going to be a little bit more specific. We're going to talk about what the graph does from quadrant 2 to quadrant 1. Well, the first guy we said was growth. So that means that function rises from quadrant 2 to quadrant 1. The second function we said was exponential decay. That means it falls from quadrant 2 to quadrant 1. Our third function is growth. So again, rises from quadrant 2 to quadrant 1. And our last function is decay. So it falls from quadrant 2 to quadrant 1. And we don't need to graph it to see that. We saw that from above. Let's talk about our domain. Now, what I notice from these two functions here is that there are no breaks in the graph. There are no gaps in the graph. I notice that the graph starts at negative infinity along the x-axis, and the graph continues and will continue until positive infinity along the positive x-axis. Same thing with decay. We are starting anywhere along the x-axis, negative infinity, all the way to positive infinity. We are able to find values. Our exponent, our domain, our x value is unlimited. So we are going to write it as the set of all x such that x is an element of the reals. And again, that is something that is the same for every exponential function, no matter the base, no matter the coefficient. Our domain is the same for all of them. Okay, so interesting that the number of x-intercepts, that was the same for all of them. The end behavior, the basic end behavior was the same for all of them. It was different for rising or falling. And the domain is the same for all of them. Let's finish off with the range. And we can see again from above that if we look at our y values, that none of our negative y values have any place here. All of our y values start from here, not at the x-axis, but just above the x-axis, and then up from there. Same thing here. All of our y values are positive. We have no negative y values. So when I go ahead and write the range, we're going to write the set of all y. Let me just clean that up a little bit. Our range is the set of all y such that y is greater than 0. The set of all y. So we're not going to say greater than or equal to because it doesn't actually touch the x-axis. but our range is all positive values of y. And again, it is the same for all of these functions. Our range is going to be the same because no matter the a, no matter the b, those are all going to have the same characteristics. Now I'm going to prove it to you. So what we're going to do is we're going to go to our equation or go to our calculator, and I've already put these 4 functions in there. So 4 times 3 to the power of x, 2 times 1/3 to the power of x, 7 to the power of x, and 1/5 to the power of x. And I'm going to graph all of these functions together to start, and then we're going to look at them individually. So let's go ahead and look at the graph. Okay, so there's got all 4 of them in there. And let's go ahead and graph those. Okay, so there's our first one, our exponential growth. That's our 4 times 3 to the power of x. Here's our 2 times 1/3 to the power of x, exponential decay. There's our third function, 7 to the power of x, exponential growth. And our fourth function, 1/5 to the power of x. Okay, so you can see that all of those guys, all the same shape. So, I mean, the exponential growth and the exponential decays look a little different, but they all have that same curve. So if we go back and look at those characteristics, the growth, decay, we got that right. We could see that. Number of x-intercepts. It's hard to see on the calculator because it does look like the function actually touches the x-axis, but it doesn't. Okay, so none of those have any x-intercepts. They are not crossing the x-axis at all. Our next characteristic is the y-intercept. We're going to talk about that in 1 second. Here's our end behavior, and indeed we can see all of these functions all start in quadrant 2. The exponential growth rise into quadrant 1. The exponential decay fall into quadrant 1. We can see our domain is x is the element of the reals. Okay, we start at negative infinity and end at positive infinity. There's no breaks or gaps or anything. The variable is, or the exponent is unlimited. It can be whatever it wants. And then again, we can see with our range, there are no negative y values. These functions only exist in the positive values of y. So y is greater than 0, never crosses the x-axis. That's why it's not greater than or equal to, it's just greater than. So when we graph all these functions, we have now confirmed all of these characteristics that we wrote in the chart. Let's do the last one. And the last one is going to be our y-intercept. And let's look at each of our graphs separately. So I'm just going to graph these one at a time. I'm going to start with the first one. We're going to start with 4 times 3 to the power of x. Let's look at the graph of that one. And let's look at where the y-intercept is for that one. So to find the y-intercept, we can put in an x value of 0. And when x is 0, y is 4. So our y-intercept for that function is at 0, 4. Great. Okay, we're going to hold on to that for 1 second. Let's look at the next guy. So we're going to turn this one off, and let's look at our second function. 2 times 1/3 to the power of x. Let's graph that one. Exponential decay, there it goes, looks good. We're going to hit trace and put in 0 for our x value. Our y value is 2. So we have our y-intercept at positive 2. So let's write that down. Interesting. Interesting. Hopefully we're seeing a connection. I notice this, 4 times 3 to the x, y-intercept at 4, 2 times 1/3 to the x, y-intercept at 2. So I'm noticing a connection right away between my a value and our y-intercept. Let's look at our third function. So let's turn the second one off, and let's turn the third one on and graph that. There it is, 7 to the power of x, lovely exponential growth. Let's hit trace and put in 0 for our x value. Our y value is 1. So our y-intercept for our third function is 1. Let's put that in, 0, 1. Now, is that connected to our a value? Well, it looks like for this one, it looks like we don't have an a value, but we actually do. Another way that we could write this function, we don't usually do this, but 1 times 7 to the power of x. Usually when we have a coefficient of 1, we don't write it, but it is there. So again, it actually works out. Our y-intercept is again connected to our coefficient. It's the same. Let's have a look at our final function at our 1/5 to the power of x. Let's have a look at where its y-intercept is. So put that one on and let's graph it. Exponential decay falls from quadrant 2 to quadrant 1. We'll hit trace, and there is our y-intercept again. And again, it's at 1, which makes sense because we'll notice with this one, it looks like it doesn't have an a value, but it does. This could also be written as 1 times 1/5 to the power of x. We just don't write a coefficient of 1, but it is there, and so our coefficient does indeed connect to our y-intercept. So let's do a quick summary of what we did. We looked at our base to determine growth or decay. If our base is greater than 1, exponential growth; between 0 and 1, exponential decay. We never have x-intercepts. Our y-intercept was connected to our coefficient. Our end behavior is always quadrant 2 to quadrant 1. It rises if we have growth. It falls if we have decay. Our domain is always x is an element of the reals. Our range is always y is greater than 0. Okay, and again, you can always graph the function to see what some of those characteristics are. You can always go to your graphing calculator, put the functions in, and see what it looks like. But I've also given you some key details to look at that you can get some of the characteristics without graphing. On the next page is a lovely summary of what we just talked about. Here is the form of our exponential function, a times b to the x. We know a and b are positive and b won't ever be 1. Our domain, always x is an element of the reals. Our range, always y is greater than 0. They're all going to have a similar shape. They're not going to look exactly the same, but all the exponential functions are going to have that same shape. An exponential function does not have any x-intercepts. Now, we didn't talk about y, so let's talk about y. Since there is no value of x that you can substitute into the function that would make the y value equal to 0. If you have a positive base, there is no way that you can take any base that is a positive number and raise it to an exponent and have that be equal to 0. It is impossible. You cannot take a positive base and raise it to any exponent and get 0. This can never work, which is why we never have a y value of 0. That is why we never have an x-intercept. The y-intercept is always connected to our a value, to our coefficient. And again, don't forget that if it looks like there isn't a coefficient, so let's back up and look at these guys again. If it looks like there isn't a coefficient there, there is one. It's 1. So it's always a times b to the x. If a is 1, we don't always write it. The end behavior is always extending from quadrant 2 to quadrant 1. If b is greater than 1, we have increasing function or growth, so it rises from quadrant 2 to quadrant 1. And if b is between 0 and 1, the function is decreasing or exponential decay, and the function falls from quadrant 2 to quadrant 1. That is lots of information about exponential functions. So what we're going to do is put it into practice with some equations. In these examples from A, B, and C from number 1, here's what our task is. Our task is to write the equations for the following exponential functions. Now, we know from above that the equation is always going to be of the form y equals a times b to the power of x. That's always what our equation is going to look like. So our job in this question is to figure out what A is and what B is. Now, I know we're given a table here, and in chapter 5, when we gave a table, we did a regression. That's not what we're going to do here. We're going to think about what some of the key characteristics were, and we're going to look at the chart to help us determine A, B for our equation. Let's start with A. We saw from above that A is related to the y-intercept. A, right there, always the A value, y-intercept. Well, how do we find the y-intercept? The y-intercept is always where x is equal to 0. So if I look on the chart, here it is. This is what I'm looking for. X is equal to 0, y is equal to 8. There's our y-intercept. I'm going to focus in on the y value of the y-intercept. There's our A value. So I know for this exponential function, it's going to be y equals 8 times something to the power of x. Because our y-intercept is connected to our A value, since our y-intercept is 8, our A is 8. Now, let's look at what our base is going to be. Let's have a look at what the y values are doing here. Our y values, let's have a look at them. 8, 4, 2, 1, 1/2, 1/4. Here's what I notice is happening. These y values, as we are going from x values that are going into quadrant 2, right? They're getting bigger. The y values are getting smaller. The y values are decreasing. That tells me that we have exponential decay here. To figure out how it's decaying, what we're going to do is look at what is our base. What are they decaying by? And the easiest way to do that is to just divide our consecutive terms. So what I mean by that is I'm going to take this 4 right here, and I'm going to divide it by the 8 right there. 4 divided by 8 is 1/2. Let's do that again with our next pairing. 2 divided by 4 gives us 1/2. So we went 4 divided by 8, 2 divided by 4, 1 divided by 2 is 1/2. Hopefully we're seeing a pattern here. This division gave us 1/2. The second division gave us 1/2. The third division gave us 1/2. If I went 1/2 divided by 1, it would give me 1/2. Our base here is 1/2. So we recognize that it's decreasing, and then we just divide consecutive term to see what it is decreasing by. And in this case, our base is 1/2. Makes sense between 0 and 1, so it's exponential decay. All right, there's our equation. That's it. That's all we want to do with this question. We want to write the equation. Let's have a look at part B. We're going to go a little quicker with part B. Y equals a times b to the x. A is connected to our y-intercept. Our y-intercept is where x is equal to 0. Here it is. Here's our y-intercept. We want to look at the y value that's connected to that. That's going to be our a value in our connection, or in our equation. So we know it's going to be 2 times something to the power of x. And don't forget your exponent of x. That's very important in an exponential function. Okay, we got to figure out our base. 1 over 18, 1 over 3, 2, 12, 72, 432. I notice that as my x values get bigger, so are the y values. The y values are increasing. This is exponential growth. So my base has to be bigger than 1. Again, to find the base, we're going to divide consecutive terms. So we're going to go 1/3 divided by 1 over 18. And I know that's kind of weird to do, so let's go to our calculators and do that. So we're going to put it in brackets, 1/3 divided by 1 over 18. And we get 6. 1/3 divided by 1 over 18 is 6. I like that. 6 is bigger than 1, but let's keep checking. Let's try 2 divided by 1/3. Again, that's kind of weird to do, so let's do that in our calculators. 2 divided by, 1/3. Notice I'm putting the fractions in brackets, and that gives us 6. Ooh, looks good. It's giving us a 6. Let's go 12 divided by 2. 12 divided by 2 is 6. 72 divided by 12 is 6. 432 divided by 72, that's a big number. We could check that on our calculator if we wanted to. 432 divided by 72, yeah, gives us 6. Great. So our base there would be 6. It's our common factor, and it's a number bigger than 1. There's our base. In part C looks different, but it is the exact same thing. It's just given to us in a graph form rather than in a form of a table, but same thing. Y equals A times B to the X. A is still going to come from our y-intercept. B we're still going to find by dividing consecutive terms. So even though it's a graph, we're still going to do it the same way. Our y-intercept for this one, it's where the graph crosses the y-axis or where x is equal to 0. There it is right there. We're going to focus in on the y value. The y value there is 2. So this is y equals 2 times something to the power of x. Don't forget that variable in the exponent. Okay, I can see that this is exponential growth just even by looking at the shape of the graph. I can see that it's rising from quadrant 2 to quadrant 1. So this is going to be exponential growth, which means our base has to be bigger than 1. We want to find what that base is going to be. So I'm going to divide my consecutive y values. We're going to go 2 divided by 1/2. We can put that into the calculator, see what we get. 2 divided by 1/2. That gives us 4. I like that. It's bigger than 1. That gives us 4. Let's check our next consecutive terms. That would be 8 divided by 2. And 8 divided by 2 also gives us 4. So our common factor there is 4. That means our base is 4. In part 2, we are also writing equations, but in this case, instead of being given a table or a graph, we are just given some information about the exponential function. Let's read 2a. In 2a, we are given that it is an increasing exponential function. Okay, great. That tells me that b is bigger than 1. It has a y-intercept of 4. Oh, super. That tells us that a is 4, and where for every increase in 1 in the x values, the y values increase by a factor of 9, which means if I was to divide my consecutive terms, every single time I get 9, there is our base. So all we have to do is take what we are given and put it in the form y equals a times b to the x. Our y-intercept is 4, so a is 4. We have an increasing function, and it's increasing by a factor of 9. Our base is 9. Our exponent is x. 4 times 9 to the x. And finally, part B, a decreasing exponential function. Okay, that tells me that b is between 0 and 1. Has a y-intercept of 1. Awesome. There's our a value. A equals 1. Where for every increase in 1 of the x values, the y values decrease by a factor of 3. So be very careful with this. You're going to want to say, because they decrease by a factor of 3, that the base is -3. But I told you from the very beginning, we can't have a base that's negative. So what it means when we say it decreases by a factor of 3, that's like it divides by 3 every time, or our base is 1/3. 1/3 is between 0 and 1, and that would mean that it goes down by a factor of 3 every time. Our equation then here is taking on the form a times b to the power of x, y equals 1 times 1/3 to the power of x, and you could even then simplify that to simply 1/3 to the power of x. Usually when we have a coefficient of 1, we don't write it. That covers the connection between the equation and the graph of an exponential function.